afternoon, right. So the last class we looked at two-way ANOVA, if you remember, right. So that was very generic in the sense two factors at multiple levels. So today we are going to focus on only two levels but multiple factors, and the real idea here is like kind of setting up screening experiments, okay. Typically if you remember, if you are doing some experiments, you come up with an experimental protocol. Have you ever done that experimental protocol? Some of you? None of you are aware of experimental protocol, right? The steps you take while doing an experiment, it is fixed, right? It is fixed, and before you start up a large scale experiments, you do some trial runs, right, and these are like screening experiments, trial runs to understand what factors are important, what are not important from my analysis, and that way what you typically do is you reduce the number of experiments that you can conduct, because you have only limited resources. Remember, you cannot conduct, and if the factors are too large, then the experiments interactions become way out of control, be multiple bilinear, trilinear, all those interaction terms, okay. So that is where we are going to talk about what is known as 2k factorial, 2 power k factorial designs. So as I said, k stands for the factors, each factor has only two levels, plus and a minus. Typically factor screening experiments, it is a preliminary study, these experiments are only for doing preliminary studies. So the objective is to identify important factors and their interactions, that is the objective, okay. So interaction of any order has 1 degree of freedom, meaning because you will have, so interaction term AB, the minimum, what is a minimum thing, how many degrees of freedom for an interaction term in two-way ANOVA, P minus 1 into Q minus 1, here what is P and Q, P and Q, what is P and Q, 2 levels, all of them are 2 levels. So all interactions has only 1 degrees of freedom, okay. So very little freedom, degrees of freedom for interactions, and factors need not be on a numerical scale even, it could be a 0 or on, like a logical plus or minus, you need not have at multiple levels, either it is on or off, that factor is involved or that factor is not even involved, it need not be on a numerical scale, like in ANOVA, in two-way ANOVA we said two factors at multiple levels. So you want to actually numerically say this is at 25%, 50, 75, etc., or give numbers to the values. Here in two-way ANOVA it is like a switch, either it is on or an off switch, that is the two levels, okay. So typically we label it as plus and minus, that is absence or presence of a term, the lower and higher, the two switches, the logics, okay. And we typically take again the assumption that the interactions all of them are additive, and we fit a model similar to that of ANOVA, two-way ANOVA, it is the same model as that of two-way ANOVA, except that now we are talking about levels to be just 2 levels, okay. The idea is these are screening experiments, quick ways to determine which interactions are important and not important. Is the setting clear everyone? Here beta 1, beta 2 are main effects and beta 1, 2 is the interaction effect. So let us take a simple 2 power 2 experiments where k equals to 2. So you have how many experiments you do? 4, okay. I told you even earlier, if you are not doing all these 4 experiments, but if you want to analyze individual, you may end up doing more number of experiments. Let us say if I want to do RCBD, I can do RCBD block A while looking for B and block B while looking for A. So I can do RCBD experiments, then I would need 2 RCBDs, typically 6 experiments, and you will never be able to learn about interactions, okay. So the advantage of factorial experiments or design is you get to know the interactions and at the same time you conduct lesser number of experiments, okay, compared to looking at one factor at a time, okay. So we are going to, so remember in the earlier case I did not consider replications, but in the last class what did we see? In 2A ANOVA what did we see? About degrees of freedom. If you do not have replications, what happens? Error degrees of freedom is 0. We saw that in 2A ANOVA. The same holds good for all factorial designs. Okay. In fact, it goes for 2 power k as well. Whatever k is, it does not matter. When you do not do a replication, the error degrees of freedom will be 0. Yesterday we saw it for a generic case, p minus 1, q minus 1. Even if you take and then add them up, the error degrees of freedom will be 0. That means you will not be able to estimate the variance at all. The variance of the estimate itself cannot be estimated if you do not have replications. So obviously you are going to have replications in all your factorial design. All your factorial design will have replications. Make sense? If you are not having replications, you have to deal it separately. We will tell you how to deal it if you do not have replications, but it is always important to have replications in a factorial design. Clear? The worst case, if you do not have, there are ways to handle it. We will look at it towards the end. But this is your 2 power 2 with replications. Now remember, what is the effect of A did we write earlier? If I want to define effect of A, anybody? Effect of A, main effect of A plus plus by 2 minus A minus B plus A minus, right? This is what we had. Now what happens if I have replications? This is without replication. What do I do when I have replication? No, I am not talking about effect of A B at all. Even when effect of A, when you have replication, how will it change? This is all without replication. This whatever effect of A we have written is without replication. What happens when you have replication? We are going to take the average of this. So that is where I am going to write y bar A plus, y bar A minus, y bar B plus and y bar B minus be the level means of A and B. So this is level means of A and B. We generally, if you do not have replicates, this is the way we compute effect of A, that we saw in last class, last or even before that. But when we have replications, then for every time you have to consider the average values. So that is why I wrote it as y bar A plus. What is y bar A plus? If I write y bar A plus, what does it mean? In this experiment, can you tell me what is y bar A plus? I have data here, right? Can somebody tell me what is y bar A plus? What is y bar A plus? So what is the value? Tell me, what is y bar A plus? Have the data, look at it, y bar A plus, what is y bar A plus? 100 by 2, how did you get 100? 36, what are the first A plus values? 36 is A plus and then 31, right? So 36, 32, 32, 3 of them, and then 31, 30, 29. It is y bar A plus, wherever A plus, then you take an average, right? Y bar A plus be the level means of A mean, and these are corresponding means. A minus B minus, what is A minus B minus? This is 80 by 3, right? And this is 100, A plus B plus is 100 by 3, A minus this thing. Got it? But y bar A plus will have 6 values. Y bar A plus will have 6 values in this case, because y bar A plus repeats twice, A plus B plus, A minus, A plus B minus. So 2 values and there are 3 replications. So there are 6 data points for y bar A, I mean A bar A plus alone, there are 6 data points. If I take A plus B plus, then it will be only 3 data points. No, we are not using, we will use it at some other point, not now, okay. So I just wanted to give you the level means of A and B and the treatment means, make sense. So I am defining it as a average, okay. Which one? Y bar A plus will be 100 by 3 plus 90 by 3, 190 by 3. So now going by that, this is how we compute the main effect of A, make sense. I am now writing it in terms of Y bar, not just A B, but in terms of Y bar. Look at this, Y bar A plus B plus Y bar A plus B minus divided by 2 minus Y minus A plus OI minus A minus divided by 2, and they are subtracted. Does it make sense? This is the same as this formula, except that now you have replaced with Y bar values, meaning your mean of the treatment values, okay, because you have more number of replications. Does it make sense, everybody? Okay. So similarly, now what we do for computational purposes, and remember these are all coded, these are all if you today use Python or R or MATLAB, these are all coded easily, right. So every time instead of coming up with what we call it as, we define what is known as a contrast. So how many treatments are there here? How many effects are, no, how many combinations are there? How many combinations are there? 4 combinations, 2 power 2 is what? 4 combinations only you have. So I define those combinations, which is A minus B minus, A plus B minus, A minus B plus, A plus B plus. These are the 4 combinations. Now any effect of A, B or AB is a combination of these 4. Any effect of A, B or AB is a combination of these 4, agreed. So now what am I going to smartly represent is, I am going to come up with indices for these 4, I mean coefficients of these 4. The coefficients are either plus 1 or minus 1. So what does this CA minus 1, 1 minus 1, 1 mean? If I write like this, what do you understand CA minus 1? Look at this, I have taken the signs, okay, clear. Now this has to be, this is my coefficient, so the main effect of A is nothing but CA hat divided by 2. Does it make sense? Does that make sense? Once I associate CA hat, I write it as, so this should be CA hat into Y bar actually. So the main effect should be CA hat into Y bar, right? Yes or no? So I can simply write it as half into Y bar into CA hat, clear? Similarly, I do the same thing for main effect B as well. So I can define, so B is this one. If you look at B, how do I write main effect of B? Main effect of B is Y bar into, so let us write simply half into A plus B plus A plus A minus B plus divided by 2, that is what I have, okay. Instead of here I would have a Y bar associated, okay, Y bar minus half into Y bar of A minus B minus plus Y bar of A plus B minus, okay, clear. So now what are the coefficient values? I can write the coefficient values. A minus B minus is negative, okay, A plus B minus is also negative, and the other two are positive. So my contrast CB is minus 1 minus 1 1 comma 1, and I can neatly represent it as main effect is y bar. See these are the the signs associated with the 4 terms in your computation of main effect. So why am I doing this? I will be able to compactly represent all your main effects and interactions rather than everything writing out here. I will be able to represent the main effect, sum squared, everything in terms of this contrast, because we know there are only 4 terms. In a 2 power 2 there are only 4 terms, in 2 power 3 there are going to be 8 terms, that is all. So if I write the contrast for the signs, the ways in which they have to be added up, then that is an index I store. I compute a plus b plus a minus b minus, take the coefficients, multiply it, I will get the answer, rather than every time coding it. You understand what is the idea behind representing this way? I am writing the same equation in a different form. Why? Because I need to store these contrast terms, take the 4 fx, I can give me data, I will compute all these 4 fx and 4 values and keep, and depending upon what you want I will change the contrast and get you the values. That is why it is powerful, okay. Computationally it is an efficient way to do, okay. So that is why I am writing it in terms of contrast, okay. So similarly I can do the same thing for AB also. AB is nothing but a plus b plus minus a minus b minus divided by 2. So that is what I have, okay. So I can do for contrast also. And you know there is a 1 to 1, so this is my contrast for all of the terms, okay. This is my contrast for all the terms, okay. So how do I write interactions? How do I write interaction of AB? Did you look at this interaction, this term? Is this different from what we learned? How did we do interactions? A plus b plus minus a minus b minus divided by 2. But how are we defining interaction here? What is interaction between A and B? How did I come up with this equation? See, if I have to write interaction A plus B plus and A minus B minus, that is only using 2 data points, right, only using 2 values. Here I have did something different. What did I do? What have we written here? Main effect of A given B plus. How is this written? What is the relation between conditional probability and intersections? We have learned what is relation between conditional probability and intersections. What is probability of A given B? What is probability of A given B? Probability of B into probability of. So I would write it the other, okay, let us write it this is easier to understand. What is probability of A intersection B? Probability of A into probability of B given A, or probability of B into probability of A given B. So that is what we are trying to do here. So main effect of A given B plus minus main effect of A given B minus. You understand how did you get this equation? Now the first itself will be 2 terms, because you will have A plus and A minus, the second you will have A plus and A minus for B minus, okay. So this is what I have, half into y bar of A plus. So you all understand how did you get the first equation? How did you get this first equation? A given B plus minus A given B minus. So A given B plus minus A given B minus. You all able to follow this interaction AB? How did I write it? The last time I wrote it very simple, A plus B plus minus A minus B, that is to show you how things are. The way to do it is using your Bayesian approach, conditional probabilities. So what do we have? A given B plus minus A given B minus. Now A given B plus itself is what? 2 more terms, because A could be positive and A could be negative. So this is what I have. Okay, and similarly the second term also has 2 terms. Now how do I expand this? A plus given B plus, how do I expand this? How do I get a, how do I expand from, how do I go from this equation to this equation? It is only a single term, you understand, there is nothing difficult here, because there are only 4 combinations, all 4 are here. Okay, what is y bar given A minus B minus is only 1, when B minus occurs A minus, so y minus B minus, and similarly A plus B minus is also, A plus given B minus is nothing but A plus B minus, there is not multiple combinations there, because we are having only 4 treatments, A plus B plus, A minus B minus, A plus B minus, A minus B plus, that is all we have. So from here to here is straightforward. Now again you have the contrast terms for all these 4. I have defined the contrast term in terms of all 4 treatments. So now I have contrast for main effect as well as the interactions. Okay. So this is what is A intersection B is B given A into probability of A, right. So if I want, so this is nothing but given, so what is A, here we are interested in, let us say A given B, right, into probability of B. What is probability of B here? So probability of A given B here, what is A given B? A given B plus, B has 2 possibilities at level 1 as well as level 0, that is level plus minus, level plus and level minus. So what is the common effect then? Common, so where will be this interaction A intersection B? Now you can write this as what A intersection B itself is. What is here? I have probability of A given B plus, right, that is one term here, that is what main effect. Then what is this and this? We are talking about the interaction between A, B at 2 different levels of B first, and then I will move. So what is the net effect? The net effect is when B minus goes from, when B goes from B minus to B plus. So that is why I write it as minus probability of A given B minus. Okay, this is the interaction is A given B, okay, in terms of A given B. So what happens? A given B itself is now interaction is B going from lower term to higher value, that is why higher minus lower, that is A given B plus minus A given B minus. Then each of them will have its own subset. Now A itself has 2 portions, that is it can happen at A plus minus A minus, and then because of the replicates I am adding the average term. So you have A given B, that is what ideally is, but A given B itself is 2 parts, A given B plus minus A given B minus, the effect is just because you are going from one switch to another. So A given B plus minus A given B minus, then that itself will branch out into another, each one of them will branch out into 2, because A itself is 2 parts, A plus and A minus. So that is how you get this equation, okay, this equation. And then when you look at the conditionals, you have only 4 data points, you do not have anything much, you have only 4 treatments. What is A plus given B plus? Only A plus B plus, then nothing else is there. So you directly write all the 4. Now you get the coefficients, I mean the contrast terms for all these 4. Okay. So now I have defined all the treatments and my main effects in terms of these 4 treatment means, and I have represented it compactly in a contrast form. So this is what I have. Okay. So now any effect is nothing but, this is the reason why I wanted to write it. Now any effect irrespective of main effect or treatment interaction effect, it is nothing but half of, look at this, half of the corresponding contrast multiplied by the corresponding mean. So this is the compact way to write. Any effect I can simply take it as half of your contrast into y bar summated over all treatments. So that is the reason why I am expanding, that is the reason why I wanted to bring this contrast. Okay. So now in one single compact form I have written all the effects, you do not need to every time break your head to look at all of this, it is just a simple half into contrast into yi bar, that is all. Okay. So that is the reason for doing this contrast business. Computationally it becomes very efficient. C changes for every effect, just the contrast term changes for every effect. For interaction it will be different, for your main effect it is different, and you just take the average, that is all. Clear? Make sense? Right. So this is the equation for 2 power 2 design, all effects simply put. What you are doing is simply this formula I have written it in a compact form, that is all I have done, nothing else. It does not mean negative means no effect, etc. Okay. This entire formula what we derived in the last few classes I have represented in a compact form, especially for 2K design, 2 power 2, it is a very simple compact form representation. And I have given formally how to do interactions using all this 4 terms instead of 2 data points. We have used all 4 treatments for computation of interactions. Clear? Why not use only a plus b plus minus a minus b minus by 2? Why did I go through all these 4 terms? Is there an advantage of using this interaction equation over the other equation? What is the other equation we did the other day? A plus b plus minus a minus b minus divided by 2. When both AB is low, AB is high, divided by 2, which makes sense, right? But why not hang on to that? Why did we use this? 2 data points. If one data point is erroneous, you cannot compute interactions, whereas here it is much more robust. I have 4, I am using all 4 treatments to compute the interaction. In the earlier case whatever I have showed you, that is also a right way of doing, just a plus b plus minus a minus b minus by 2, nobody is stopping you from doing that. How you are going from the lower to higher together as a switch, a b as a switch, there is nothing wrong, like a we can do that, but you are only using 2 data points, rather I am here using all 4 data points, all 4 treatment values, that is an advantage because it will be robust. Clear? And now the moment you write the equation in that certain fashion, in the contrast fashion, sum square treatments become pretty simple. Sum square A, sum square B, sum square C, all of them becomes pretty simple, because this is nothing but, what do we know? It is nothing but fx square divided by the, so when you take sum square contracts, this is what your sum square is, this is nothing but your effect, fx square divided by the total, which is nothing but in this case it is 4 by n. What is Ci? Ci is how much, how many levels are there? 2 levels. Ci square is nothing but 4 divided by n. So everything falls in place the moment you define the contrast. Okay. In fact this should be k squared by n instead of, yeah, it should be k square. Even if you sum up Ci you will get the same, because you see anywhere you sum up it will be only 2. Okay. So sum up ki Ci, so if you look at this equation, 1 minus 1 minus 1 1, so this is k squared, this is also nothing but, obviously this is k squared by n. K is what? 2 here, yeah, 2 factors, right? K is 2 square by n, or if you want to do it, this is also the same, 2 power k, because this is 2 power 3, this will be 8 and so on. So this is what we have here, this will be same as Ci square by n. No, this is sum squared. This is only sum squared. I am not doing mean squared at all. Mean squared will be again you have to divide it by the degrees of freedom, and in this case sum squared and mean squared will be same, because what is the degrees of freedom? What is the degrees of freedom? Everywhere the degrees of freedom will be only 1. Which one? When you compute the sum squared error, right? Sum squared will be for where will the replications, all of these averages, all of them will go for different levels. How do you accommodate for? You have not accounted for levels, you have only accounted for replications. Levels you have to account, na? That is where. So this is why you have 4 over n, okay, Ci squared by n. So this is my sum square values and the table is here. All degrees of freedom are 1, treatments, all treatments are 1, because 2 minus 1, 2 minus 1, okay, and your total will be different, your total will be n minus 1, where the n is the total number of data points accounting for replications. So you, because of your replications you will have more number of data points, that will be n minus 1, okay. So ideally this should be like k into what do we have k into p minus 1 or k p q minus 1. If you remember 2 ANOVA, that was mpq minus m, where m is the replications, it should be k p q minus 1, but all p and q are this thing. So we have that is why we have total data point is n minus 1, okay, and the error degrees of freedom is n minus 3, okay. If you do not do replications you will not have degrees of freedom at all, keep that in mind, okay. So n minus 1 should be equal to, if you are there is no replication 3, if n equals to 4 then what will happen, 4 minus 1 equals to 1 plus 1 plus 1, you will not have degrees of freedom for error if you do not do replications. If you do not do replications the number of data points is only 4, only 4 experiments, 2 power 2 only 4 experiments, the error degrees of freedom will be 0 if you do not do replications. Make sense? Clear? So this is our 2 power 2, and you can also do this 2 power 2, we start fitting a regression model. Remember you have an interaction term, okay, okay, and you can do like yesterday I showed you, you can do differentiation or you can do by rules, but in thankfully in ANOVA experiments, especially in 2 factorial experiments, the answer is factorial experiments, the answer is pretty straightforward. The factors are nothing but, the parameters are nothing but effect divided by 2. When you differentiate it and do it you will get the same answer. That is why I have directly written this beta 1 is nothing but effect of A by 2, effect of B by 2, this is AB by 2. If you differentiate it and do this you will get the same answer, but factorial experiments this is pretty simple, all parameters are nothing but fx divided by 2. So you do not need to worry about how to solve for this linear regression, what is the estimate. The estimate of coefficients are pretty straightforward, this is nothing but fx divided by 2. So the only equation which is of importance is that contrast equation. If you know the effect equation you have done everything, because once you know the effect the sum square is nothing but fx square divided by 4 by n, okay, comes out, and your coefficients are nothing but fx divided by 2. So this, that is why this one equation is what which determines your entire 2 power k experiments, and that is why 2 power k experiments are popular, because you need to do lesser number of experiments and computationally very efficient, you will get the results in no time, okay. And the degrees of freedom you will increase depending upon the number of replications. You do not need to do more number of replications, because look at this, even if I have n equals to 2, how many degrees of freedom I will have? So suppose instead of k equals to 2 what will I have, or replication equals to 2 what will I have? I will have 2 4 into 2 8 minus 1, so 7, error degrees of freedom will be 3. Even if you do one replication, you will get a good amount of degrees of freedom for error, because your number of degrees of freedom for treatments are just 1. So, the error degrees of freedom will go high. So, you will have a decent estimate of variance. So, that is why even with few replications you will be able to screen out. Okay, that is why this 2 power 2 or 2 power 3 or 2 power k experiment is very popular. Okay, that is why it is a separate topic by itself.